Well, I hope more people can show up. We'll give everybody another minute or two. Ooh, that's the winner. All right. All right. Well, 8 people said they could show up, but there's only 3 of you. So I guess we'll start anyhow. Who wants to start us off with the first question? Anybody? Don't be shy. Can you guys hear me?
Yes, I can hear you.
Thank you, Lloyd.
You're welcome.
Okay. Well, guys, I mean, Thursday nights are usually Q&As, and so if you ain't got Q's, I don't have A's. Is there anything you want to talk about for the mini project, the homework? You can even ask about next week's stuff if you've been working ahead. All right. Having some technical issues. No worries. You can type your question in, Tiffany. All right, well, while I'm waiting for you guys to come up with some questions, let me point out a few things. And this is mainly for people who are going to watch the videos as well. But if you do percentiles in Excel, you will get slightly different answers than if you do them in SAS. And it's just the way that Excel calculates percentiles. So just be aware of that different technologies calculate percentiles differently, and it's based on some of them. Like, for instance, if a percentile is supposed to fall in between 2 numbers, so for instance, in this one, if we're looking for the 25th percentile, and let's say that's supposed to land right in between the 13th and the 14th number, right? We talk about, when we put them in order, you talk about it being between the 13th and 14th rank. And that just, if you ever hear anybody talk about rank, it just means that once you put the data in order, the 13th rank means the 13th piece of data, which obviously, doesn't have to be a 13. It could be any number, right? So it's supposed to land in between the 13th and the 14th. Well, some technologies will say that your 25th percentile is the 14th number. It'll just round up because it wants to make sure it gives you a value that is greater than or equal to 25% of your data. But since it landed halfway in between, then all of those 13 numbers below it, make up 25%. Actually, they make up a little bit less, right? Because 25% would be halfway. So some technologies, like I said, will report the 14th rank, basically, as being your percentile. Some will say, oh, it's 13 and a half. And then some will even come up with a different number between 13 and 14, and they base it on kind of, it's really weird, but they do this really complicated kind of average of the two numbers that sit in those places. So instead of, just doing 13 and a half, because it's halfway in between the 13th and the 14th number, it will look at what the 13th number is. It will look at what the 14th number is, and then it'll give you some sort of average of those two things. So you can get, drastically different results based on the technology you use. Bottom line is, they're all going to give you roughly the same data value, right? They might just give you different ranks, but when you go back and look at your data, it's all going to correspond to pretty much the same data value, maybe only off by a little. So just something to know that can be weird. And I am well aware of the idiosyncrasies of Excel. So if you're doing things in Excel, your answers are going to be slightly different from the answer key that the book has, because the book obviously only uses SAS, but I don't take off for those because I know how to use Excel. Let's see. This one gives students a lot of problems. So make sure you really understand that question. You're simply just taking whatever the average is of these numbers, adding and subtracting a standard deviation from it, getting an interval, and then you're counting up how many of your numbers are within that interval. And then creating a percentage based on that. So whatever that number is, then you divide by 70, because there was 70 total measurements. And then that gives you a percentage, and then you compare that to the empirical rule of 68, 95, 99.7. And this brings me to something that I should have mentioned before. Anytime you guys are doing any kind of math, right, any analyses that result in a numerical answer, whether it's, calculating a mean or a standard deviation or a percentage, or next week when you're doing probabilities, anytime you do any kind of math, you should always, at a bare minimum, display 2 decimal points of accuracy. And I really think 4 is the minimum. And here's why I say 4 is the minimum, because if you take a decimal and convert it to a percentage, you lose 2 decimal places, right? So for instance, the number 0.2548 equals 24.58%, right? So you went from basically having 4 decimal places to only 2 decimal places. And if you had rounded this, right, if you had oh, sorry, 2, I got dyslexic. 25.48. If you had rounded this number to 2 decimal places, you would have got 0.25, which would have equaled 25%. But this is almost 25.5%. So to me, that's a meaningful difference. And even worse, if you had rounded this decimal all the way down to 1 place, it would have been 0.3, which would have equaled 30%, which is horribly wrong, right? So my point in all of this is, really, you should kind of report as many decimals as you can before it just gets kind of useless and bogs you down. 4 is usually a pretty good amount. 6 to 8 is usually the maximum that anybody ever does. But I really think we should strive for at least 4 with all of our answers. So going forward, and please, by all means, do not go back and change your homework for this week, especially if you've already turned it in. And same for the, the mini project, if you've turned it in, don't worry about it. But going forward, let's please do at least 4 decimal places of accuracy. So next week, yes, next week we get into probability. And probability can be tricky for students. And the main reason why probability can be tricky is if you interpret the wording of the question slightly differently than it was intended, you will get a drastically different answer. So unfortunately, some of these questions are written in such a way that they're not, crystal clear, and you could unfortunately interpret them differently. For instance, these questions here are often misinterpreted, and that's why I wrote this stuff after it. I don't know if I wrote this stuff after it in the Google Drive, but I probably should. But basically, if we look at this sentence, what is the probability that a white donor will not have type A blood? Some students just think that that means that you're looking for white donors that don't have type A blood. You're basically going up here and saying, okay, white donors that don't have type A blood is 32.2 plus 8.8 plus 3.2. They basically just did a simple and question, right? In probability, an and question is an intersection. So you're looking for the intersection of white patients and everything other than type O blood. And so you get these 3 percentages and you add those together. Well, unfortunately, that's incorrect according to what the question is trying to get you. Now, I can see the logic behind it and I can see the argument for it, but what this question is really saying is, what's the probability that a patient will not have type A blood given that they're white? See, this condition of being white is a given condition. So that becomes a conditional probability, which is quite different than an and, right? And would just be adding these 3. The conditional probability says, okay, we know the donor is white, so we're only going to look at the white donor. So we're only looking at these 4 percentages. Now, among those 4 percentages, which ones satisfy the question, which in this case is don't have type A? And you get these same 3 numbers. But the difference is, when you did the and question, it was these 3 numbers, but you were still looking at everybody. So you took the good, right? If you watch my videos, I talk about good over total. These 3 numbers are the good because they represent what the question was asking. And then you always take the good and you divide it by the total. And since if we thought of this as an and question, we were still looking at everything, the total would be all of this, and it all adds up to 100%. So you would literally just add these numbers and divide by 100%. But since they're already in percentages, you basically just add the numbers, right? Because dividing by 100 doesn't change it. However, when it's a conditional probability, the total is no longer everything. The total is the condition. So you would add up these 3 numbers, but instead of dividing by 100, you would divide by the sum of these 4 numbers, right? So you would take whatever this sum was, which is 44.2, and you would divide it by all 4 numbers, which is, I say 44.2 would be 80, I guess 80.2, right? So you're dividing by a different total. So that's the big thing with conditional probability. And next week, if you watch my videos, I go over that. But the same problem happens with this second one, because they say that it's now an Asian donor, so that becomes a given condition. So now you're only looking at the Asian donors, the ones that are circled in red. You calculate, you add up all the good stuff. So the good stuff is type A or type B, which are these 2 numbers. And I should make this bigger so you guys can actually see the numbers. So you add up these 2 numbers of 1.2 and 1. You get, okay, so 2.2% are the good, and the total is all Asian donors. So you would add all these together, right, and get 1, 2, 3, 3.7, 4, 4.2. So you would get 2.2 divided by 4.2, And that would be your answer for part C, rather than if you considered it just be an and question, right? That, oh, the person just has to have both of these characteristics. They have to be an Asian donor and they have to have type A or type A or B blood. Then it would just be the intersection, and you would think it was just 2.2, right? It's just these two numbers because that's the intersection of AB and Asian. But it isn't an intersection question. It isn't an and question because it doesn't say what's the probability that someone will be Asian and have type A or type B. It says what's the probability that an Asian donor will have type A or type B. And I know the English language can be very confusing because it's not a very precise language, but there is a difference between those two sentences. And the difference is in the second sentence, we're basically proclaiming that this person is Asian, i.e. you are given that characteristic. And so that becomes a given condition and you treat it as a conditional. So that's kind of one of the biggest stumbling blocks that happens next week. Other than that, it's pretty straightforward, right? All of these things are pretty easy. Let's see. Here's another one where the wording can be misinterpreted. So if we look at the data up here, we have it's government employees who have an advanced college degree, and then whether or not they're given a promotion to a higher grade position. So here is whether or not they were promoted, rejected, and accepted. And then here is if they're married. When it says both spouses are professional, it just means that they have an advanced degree and their spouse also has an advanced degree. Here, when it says one spouse is professional, that just means they alone had an advanced degree and their spouse didn't. And then here, if they're unmarried, then of course, that's just how many of them had an advanced degree. So what is the probability that a randomly selected government employee having an advanced college degree would accept promotion, right? Well, having an advanced college degree is a given. This is a conditional probability again. What's the probability that a randomly selected government employee having an advanced, right? They didn't say what's the probability that if we pick somebody at random, they have an advanced college degree and they accept the promotion. They just say, what's the probability of randomly selecting a government employee who has an advanced degree, and then whether or not, right? So this is a given condition. So we only look at this column and this column, because those are the two that, we look at all three of these columns because they all have an advanced degree. So it's basically, they have an advanced degree, what's the probability they would accept the promotion? So we add up the acceptance, divide by the total. Well, the total is all of them because all of them have this advanced degree. So the conditional kind of goes away at that point. Let's see. Oh, here we go. This is the confusing one. What's probably the randomly selected government employee having an advanced college degree has a spouse with a professional position? That's where you have to look at both spouses with the professional position. Because the one spouse is assuming it's the government employee. So that's where they just didn't explain their data really well. So this one is basically talking about this column. Let's see. This one's pretty straightforward. I suggest doing the same thing that I do here, right? Whenever you have data in a table and you have these different things that you want to find, so they give you these conditions A, B, and C, and then they want you to figure out the probability of A, the probability of B, the probability of A given B, and so on and so forth. I always think it's very helpful to visually see what A means, right? So A is the blue stripe, B is the green stripe, and then C is the yellow stripe. And it helps a lot with being able to figure these things out. So just it's a good trick. Think about it. Same thing here. I took the verbiage, English words, and basically made colors. More than 3 times means 4, 5, and 6. At least 2 times, but less than 5 means 2, 3, and 4, because at least 2, but less than 5. And then more than 4 just means 5 and 6. So when you can take English and basically translate it into numbers, it's going to make these questions a lot easier. And other than that, the only other thing that's the least bit tricky with next week is the Poisson approximation. But I talk about this in my videos, and there is code that we have here in the how-to, right? If you go down to week 4, you have code for running binomials, and then you've got code for running Poisson distributions. So it's pretty easy to just throw it into SAS and get your answers that way. All right, so that's week 4. Great question, Tiffany. All right, so we had a couple people came in late, which is awesome. You haven't missed anything. We were basically just talking about week 4 a little bit. So does anybody have a question on this week's stuff, week 3 homework or the mini project?
I have a question.
Yes, Latanya.
I'm sorry, I'm in my car, so bear with me.
No worries.
I'm not driving.
Good for you.
So I drew, or I shouldn't say I drew. I put the box. Okay, so going back to homework assignment week 3,
Yep.
3.34, where
Yep.
it says stem and leaf, and then the box plot.
Yep.
I did it, but I had such a hard time coming up with it, and I kind of copied and pasted it, but I guess it jumbled up together.
Yes.
Is there an easier way to do it? Because the way I thought about screen printing it, but it didn't look right. But it took me forever to try to figure out how to get there. And now my worry is that I won't remember how to get there, back there.
Okay, so 3.34, right? We want to make a box plot and then a stem and leaf plot.
Yes.
So in order to do the stem and leaf plot in SAS, you have to use the code because it won't make them otherwise. It's the only way to get it to do it. So let's load our data. We've got 3.34. Add our analysis variable, which of course is just rates. And then if we run this, we get our lovely little box plot, which is the other part of it. And you can make it horizontal if you want, because I don't care, but I always make my horizontal. Okay, so that's the box plot part. That's easy. The stem and leaf plot, you have to click on code, click edit, and then go up here to our week 3 code, right? And where is it? That's the quantile plots. Did I get rid of it? Oh no, that's right. I think we originally did it in week 2, but I need to move this. Modes. Here we go. Histogram. Box plot, Semileaf Plot. Okay. So let me move this. We used to have a question on our homework in week 2 where we had to make a box plot. A Semileaf Plot, and we don't do that anymore. So I gotta move that here to the right week. Okay, so if we copy this data, this code to SAS Studio and just put it in down here, and then we just need to fix it. Okay, so ODS graphics off and ODS select plots, SS plots. What that does is that turns the graphics off that basically allows this thing to give us the Semileaf plot that we want. So we don't want this, right? Because that's a different ODS thing. We don't need any of this, but we do need to know where our data is, and that's where our data is. So if we copy that and come down here and put that here, that will make sure that we get the right kind of data. And then our variable was rates. So we don't need any of this junk because that was for a different question. So instead we need rates. Now that I've kind of stolen everything I needed from the original. See, that's why I like to run the data, and then it gives me the basic code for that stuff. And then I can pick apart the things I need for mine, which is basically wherever my data is located and my variable name. And then everything else is just junk that I don't need. So if I run this, fingers crossed, there's my stem and leaf plot. Now, if you do what you did, which is you highlight it like this, copy it, and then go to a Word and paste it, what happens is it gets all jumbled because this page isn't as wide as the other one, and things are kind of wrapping. Your text is wrapping around, instead of page breaks. So it looks horrible. It doesn't work because you can't tell what's going on. So what you want to do instead is just use the snipping tool and just take a snip of the box plot. Don't need all the other junk, right? We can I'm sorry, the stem and leaf plot. We don't need anything else. So there it is. And then we can go into Word, and then we can paste it, and it stays all nice and pretty. Now, Latanya, if that is confusing, and I wouldn't be surprised if it is, you can always just do this manually in Excel, right? You can take your data, you can sort it, and then create your own stem and just put in all the leaves. Because this means, if you didn't know what a stem and leaf plot tells you, this 0 just means that you have 40 in your data. Then you have 41, 46, then you have 4 49s, 49, 49, 49, 49. And this tells you all the 50s, right? All the 60s and all the 70s. So once you have everything sorted in Excel, it's really easy to just create your own stem and leaf plot in Excel by just taking, the stems and putting in the leaves. Does that make sense? Latanya?
It does. Sorry, I was trying to work this phone.
No, that's fine.
Yes, it makes sense.
Okay. So you think you can be able to do it either one way or the other?
Yeah, and I think that when you go over it in class, and sometimes I get lost in the steps, and I have tried to put in code repeatedly, and sometimes it works and sometimes it doesn't. So looking at you take out stuff is really helpful.
Sure. Good. All right.
Yeah, I got it last time. It just I guess, like you said, I copied and pasted, and I agree, it kind of does look jumbled compared to your example.
It just gets hard to read at that point, unfortunately.
Okay. And then my last question is on, I think it is 3.56, and I think that it is letter E as in boy.
Okay.
You said my standard deviation was incorrect.
Let's see. Yeah. For the whole set. Yeah. For some strange reason, you had a really weird standard deviation. So for part B, you're supposed to get the standard deviation for basically everything all together. You no longer have them grouped. So that was 54, right?
I think it was 56. Let me see.
56? Sorry, 56.
That's 56.
Yeah,
yes, 56. It was 56.
Okay, which uses the data from 55. So if we go to summary statistics and grab 50, I called it 56, even though it's 55. And then we're going to add in expenditures, right? And if we use the classification variable, actually we don't want classification, we want group analysis by. If we group it by number members and run it, this is how we get the individual ones, right? So these are the standard deviations for each of the individual sets where there's 1 member, 2 members, and so on and so forth. But for part B, all we have to do is get rid of this grouping number and then rerun it. And then now you can see the number is 83. It means it's using all 83 pieces of data. And there's the standard deviation for like the whole set of data, not broken up by groups. And your answer was like one point something, if I remember correctly. So it's, I don't know where you got it, but it was way off. So I think you must have clicked something or done something weird.
I agree. Looking at your answer compared to mine.
Yeah, I usually try and give students some advice based on their answer, but I apologize. I had no idea how you got that number. I'm assuming you must have like grabbed the wrong data set or done something, because it was so far off. It had to have been something weird.
I think I did the individual one, or
Yeah.
did and like one of the many individual ones instead of did the I didn't take that numbers out, the numbers member. So I think that's what I did incorrectly.
Okay, sounds right. Cool. All right, Prince, I see you've got a question.
Yes, my question is on that same question, but it's actually part C.
Okay.
Do you want a narrative, or how do you?
You can describe it in words. You can describe it with a formula. However you want to describe it. The bottom line is there really isn't a way to do it and get an accurate answer without an extremely advanced calculation. So I had mentioned this last week. I think what the book is trying to teach you with this question, right? I always try and think of, all right, what the hell is the book trying to teach? Because sometimes I read these questions and go, what the hell is the point of this? I think what they're trying to get to here is, last week we had the question where we had the means of a bunch of different subsets, and then we did the mean of the entire group. And then it asked, okay, describe a method where you could get that same answer for the entire set of data, but only by using the means from each of the groups. And we went, oh, that's easy. That's a weighted mean. So we take the mean of group 1 and we multiply it by how many things are in group 1. And we take the mean of group 2 and we multiply it by how many things are in that set. We do it over and over again. Then we add all those things together, and then we divide by the total number of things. And that's what's called a weighted mean. And it's very easy. And it gives us the exact, 100% accurate mean of the entire set of numbers. Well, if you tried that same thing with standard deviations, it ain't going to work at all. And even if you kind of unravel the standard deviation formula a little bit and kind of do that and work with variances and stuff like that, you can get closer, but it's still not going to work perfectly. So I think what they're trying to show you is, that even though these are two statistics, they don't work the same. You can't manipulate them the same way.
So I guess what do you expect to see in that for that answer?
I would expect you to maybe describe a method that gives you an approximation, get you pretty close, and then mention that it's not accurate.
Okay.
Because that's all I would want you to learn from that question is that, let's say you came across some data that was presented to you as part A, right? They only gave you the part A results. They didn't actually combine it and give you the part B result. But you were curious. You wanted to know what the part B result was. Well, describe a method where you could get a pretty good idea of what B is. Even though it's not going to be precise, you can get a pretty close answer using this method that you described. That's kind of what I'm thinking.
Okay. All right. I'll think of something.
Okay.
Thank you.
Yep. Anything else?
Those were my questions. Thank you.
Of course. And Prince, don't waste a lot of time on part C. I had mentioned before last time that if you look at the formula for a standard deviation, you can kind of unravel it, right? So a standard deviation, you take the sum of every data value minus the mean squared, right? Then you divide that by n minus 1. Then you take the square root of the whole thing. And that's a standard deviation.
Yes.
So if we wanted to unravel this, right, if we wanted to unroll it the first thing we have to do is square both sides to get rid of the square root. So if we look at just the sum of each data value minus the mean squared all over n minus 1, that's going to be s squared, which is the variance. Well, if we look what's happening here, we have a bunch of what are called deviation scores, because it's how far a data value deviates from the mean, because we take that data value, subtract the mean from it. So that gives us the difference between those two things. It's deviation. We square that, then we add all that crap together and we divide by how many things are in that set, right? Minus 1. So let's say, group 1 had 12 items. We know that we're going to add up all these deviations. We're going to take all these deviations, we're going to square them, we're going to add them all up and then divide by a number. Well, adding them all up and dividing by a number, that sounds an awful lot like a mean or an average, right? Because you add a bunch of things, you divide by how many you have. That's kind of similar to an average. So if we take the variance, right? So if we take all those standard deviations and we square them, then the next thing we do is we multiply them by their sample size minus 1. Oops, squared equals the variance times n minus 1. I remember n is going to change for each one of our subgroups because it's how big they are. So now if we take the variance, we multiply by the subgroup size minus 1, it gets us this sum of all of their deviations. And then if we did it for the other group, of course, it's going to be a different X bar, right? Because this is going to be the mean from the first group. This is going to be the mean from the second group. So this is the variance of the first group, the number of things in the first group. And then we're going to have the variance of the second group, the number of things in the second group, right? So if we did this with all of them, this idea of taking the standard deviation, squaring it, multiplying it by its sample size minus 1, did all of those. If we got to the bottom and added all of this together, it's pretty much the same thing as adding all of these together. But here's why it's not accurate. Each one of these is using the mean from the group, whereas if we were going to do the standard deviation for real, it would use the mean of the entire set of things. Well, we know that the mean of each subgroup is going to be different than the mean of the whole group, but it's going to be pretty close. So that's why the answer is still going to be pretty close, right? So when we do these multiplications and we add them all together, like over here, then all we have to do is basically finish the normal formula. So now that we have this big summation, we then divide it by the sum of everything minus 1. That's why it's a capital N. So if there were, 75 total pieces of data, 12 in this group, 14 in that group, so on and so forth, then we would divide by 74. That would give us the variance, and then we take the square root of it, and that gets us back to the standard deviation. And it's a pretty damn close approximation. That's the process that I would go with, and the process I would describe. It's the least complicated process that results in a fairly accurate approximation.
Makes perfect sense.
Awesome.
Thank you.
Yep.
You know what, Dr. McBride, I lied. I got one more question.
Nope, sorry, you said you were done. Go ahead.
Okay, so for the mini project,
Yeah.
I did all the individual steps. So when I think, and I don't want to misinterpret it, you want a summation of the assignment as a whole, is that correct? Or
No,
do
and I'm
you
glad you
want-
asked. You should
Okay.
be noting every response. So every time you do something, so basically you do this bullet point of generating some frequency tables, and then just give a quick couple sentence kind of summation of what you found. Was there anything similar amongst these 3 tables? Was there anything vastly different about those 3 tables? Was there anything interesting about those 3 tables? Just a basic, quick blurb. So, I always tell my students, when you're doing this stuff, envision that you work for somebody who is completely oblivious to statistics. They know nothing about statistics, but they ask you to go and generate all of this. So then you're going to present your findings to them, but you better give them some explanation and point out some things, because remember, they don't know anything about statistics. So, so I'm not expecting you to, describe everything from, the ground up, but give them enough insight into the results that it actually means something to them, because they don't have a firm grasp, they haven't taken a statistics class, so to speak, that kind of thing. That's what I'm looking for. So for every single bullet point, you should just have a quick little kind of executive summary, just a couple sentences going, hey, this is what this stuff means. Based on this, we can see this pattern or blah, 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 that kind of thing.
Okay, so I just want to be clear for myself. When you say a quick blurb, do you mean like 2-3 sentences, or do you want us to go down a rabbit hole and really explain it?
2-3 sentences is totally enough. That's all. I just want to know that if you were stuck in an elevator with your boss, they talk about the elevator pitch, where you have to be able to tell somebody what you're thinking in a short enough, concise enough amount of time that by the time you get to the next floor, or whatever floor you're getting off, they understand it. That's what I'm looking for. Just a quick little elevator pitch of, here are my results. Here's what they mean. Ding. All right. See you next day. That kind of thing. So just quick, down and dirty, just describe what's going on. 2 or 3 sentences tops.
Okay. Thank you.
Yep. Now, before I forget, because so many people get this wrong, it really, really is, don't say it bothers me, but it's worrisome how many people get this wrong, is we need to talk about these variables and what kind of variables they are, because a lot of these questions ask you to do things on specific things like categorical variables, right? They want you to work with categorical variables. And then they want you to work with quantitative variables, right? So you need to know the difference between the two. So first of all, the first variable that you see in the data set is the subject. And as I wrote right here, completely ignore that. All that is a locator number. It means nothing. Then there's a variable called treatment. And that variable is made up of either zeros or ones, right? It's just a bunch of zeros and ones, which throws some students off because they see a number and they go, oh, that's a quantitative variable. No, it isn't. Damn it. That's just a categorical variable. The zeros and ones are just there to represent words. 0 just means placebo. 1 just means treatment. So literally that variable, when you see 0, they could have just replaced it with the English word placebo, and they could have replaced the 1 with treatment, right? So that is still just a categorical variable. All it does is describe something. Gender, of course, everybody usually understands that that's a categorical variable, right? Because it's made up of words, male and female. And then family history is also usually pretty easy to recognize as a categorical variable, because again, it has letters, right? So if you look at that variable, you're just going to see PS, MS, BS, and N, meaning one of these 4 categories, right? Categorical variable, category. Of course, age is numbers. That's a category, that's a quantitative. Your BP before and your BP after are also quantitative. And technically, all 3 of these are continuous quantitative variables, because all 3 of those are measured. You measure someone's blood pressure, and you technically measure your age because it's a measure of time that has elapsed, right? Now, some people treat age as a discrete variable instead of a continuous variable, because you're either 35 years old or you're 36 or you're 37. You're not really measuring, you're counting how many years have passed. And that's true. You can argue one way or the other, but technically you're still measuring their age. The person is just reporting it as a discrete count, but at its fundamental, core, age is a continuous variable because it can be measured at different units of measure, right? It can be measured in smaller and smaller increments. You can say you're 35 years old, but then you could say you're 35 years old and 7 months, right? Or you're 35 years, 7 months, 2 weeks, and so on and so forth, right? So you can measure your age with increasing levels of accuracy, ergo it's measured, ergo it's continuous. And I always, bring it back to a simpler thing so you can see the correlation, how they match up, the similarities between the two. Measure your height. Oh, I'm 6 feet 5 inches. Oh, I'm 6 feet 5.5 inches, right? So you can always measure with more and more accuracy. Of course, if we were in the metric system, then of course you can go from meters to centimeters to millimeters and so on and so forth. So things that are measured are continuous, and age is technically a measurement. So with that in mind, you should be able to know how to do the first one because you know what the 3 categorical variables are. Cross tabulations, as I said here, must be done using 2 categorical variables only, right? They don't work with quantitative variables. So again, for the second one, you have to pick categorical variables to do your cross tabulations. Then this one, the Pareto chart, they even tell you family history BP is a categorical variable. Then this one, a 5-number summary for all 3 quantitative variables. Well, we just described that, right? These are the 3 quantitatives. So you do a histogram for those same 3. And then the last 2, they explicitly tell you what to do, a scatter plot between this and this, and a scatter plot between that and that, right? So I just want to point that out because far too many people get a bunch of these wrong because they're using the wrong variables, okay? So you need to know the difference between quantitative and categorical. All right, that's all I can think of. Unless you guys have any more questions, we can call it a night. Okay. Don't forget, you don't have to turn your mini project in to Turnitin because you're not really writing a lot. So we don't have to worry about you plagiarizing someone else. And besides, just like the homework, since everybody has the same questions, if you turned it in, you would have a really high similarity score. But you do have to turn in your article critique to turn it in. That's the only thing you're turning in is the article critique. And that is not due until next Thursday. So don't worry about that. Get your mini project done first, get your homework for this week done, then jump on week 4 homework and the critique. And then if you haven't already done so, please, please, please go fill out the doodle poll so we can figure out the time that we'll meet next week, right, on Tuesday the 7th, because the 6th is a holiday. And then the following week, we're going to meet Wednesday the 15th instead of Thursday the 16th. Or did I put Friday the 17th? I can't remember which, but whatever day I chose for that week, we just aren't going to be there on the 16th.
Dr. McBride, was I supposed to do something special? Because when I went in and looked at the doodle thing, I only seen today's thing. And it could have just been me completely, but I didn't see the option for all the other days.
I think maybe you have to scroll farther to the right to see them.
Okay, thank you.
Yep, and then you get the 7th, and then if you scroll further, you get Wednesday the 15th.
Okay, thanks.
Yeah, so just go back, and I think you can just add more. I don't think you have to redo it, but if you have to redo it, just go ahead and redo it, because it doesn't matter, if your name shows up twice. Just don't. It doesn't matter. I mean, if you redid the whole thing, it doesn't matter because day's already come and gone. But just make sure you give me the times for the 7th and the 15th.
Okay, thanks.
Cool. Okay. Anything else? All right, folks. Thanks for showing up. Sorry again for missing yesterday. The recording should be available pretty soon. And we will see you next Tuesday.
Thank you.
Yep, you're welcome, Prince. Thanks.
Thank you.
Thank you.
Good night, everybody.